Acid-base strength. Here we have a graphical representation of the pKa value, which is showing the increasing acidity pattern towards the left side, showing the different materials, particularly organic substances that are included in the important categories of the bronzate-lowry acids, are showing the different ranges of the pKa values. So this pKa value determines the acidity of these acids, and now let's discuss that what is the pKa value and how we can calculate the strength of the acid and bases. So the strength of acid or base depends on the extent to which it ionizes in water. So the strength of an acid or base is basically depend on the extent to which it ionizes in water. Although there are numerous examples of the solvents that are used in place of water for making different kind of acid and base solutions, but usually chemists use water as a solvent to calculate the acid-base strength and relative evaluations. And usually chemists discussed acid and base strength in relation to the water because they use it so widely as a solvent. Chemists used the autoionization of pure water to determine the values for the concentration of acid and basic solution. So the autoionization of water that is usually for pure water is used to determine the acid and base strength for the acidic and basic solutions. So here what is autoionization? Autoionization is the reaction of two molecules of water with each other to give a hydronium ion and hydroxyl ion. For this reaction, amount of autoionization is extremely low at 25 degrees centigrade, and it is almost 10 to the power minus 7 molar or moles per liter. So these small fraction of the molecules which are undergoing the process of autoionization within the water. So this amount of hydroxyl ion or hydronium ion within the water, so this molarity is considered as neutral solution. If we add that is more acidic than water, it can make the solution more acidic, whereas if you add a compound that is more basic than water, then it can make the solution basic. As these number of moles of water molecules are undergoing the process of autoionization, so the concentration of the two generated species is 10 to the power minus 7 molar each, and the product of the concentration of hydronium ion and hydroxyl ion is equal to an equilibrium constant known as Kw, because the process is equilibrium, and the constant is given as the product of the concentrations of hydronium ion and hydroxyl ion. So the total product is equal to the 10 to the power minus 14, because the concentrations of the hydroxyl ion and the hydronium ion are equal in a solution. You can easily calculate the concentration of both. That is equal to 10 to the power minus 7 molar for each component or the ionic species that is produced through the process of autoionization. Because the product of the two concentrations is a constant, when you add hydroxyl ions to water, the concentration of the hydronium ion decreases by whatever amount is necessary for the product of the two concentration, that must be equal to the concentration, that is 10 to the power minus 14, because the hydronium ion concentration can span a very wide range of values from greater than 1 molar down to less than 10 to the power minus 14 molar. So the scientist or the chemist usually measure the concentration of the hydronium ion, and the range is wide. So for this purpose, a logarithmic scale is used, which is known as pH. So pH is actually a logarithmic scale, and the pH values give the concentration of hydronium ion within a solution. Therefore, measuring the pH of a solution is a means of quantifying the acidity of the solution. So if we measure the pH of a solution, it means we are going to quantify the acidity of that solution. Chemists define this measurement as the negative logarithmic value of the concentration of hydroxyl ion represented by pH, that is the negative logarithmic value of hydronium ion, and this log is of base 10. If we observe closely that the hydronium ion is actually composed of one water molecule, that is neutral, and one hydrogen or proton. So this hydrogen ion can be replaced with the hydronium ion. So we can write the pH is the negative log of hydrogen ion concentration. If hydrogen ion is present in an aqueous solution, remember that it is actually the hydronium ion. So now let's consider an example that is showing the general reaction of an acid with base in, that is actually water. So here it can be hydrogen chloride or hydrochloric acid. So we can write acid because it is donating the proton, and water is acting as base because it is accepting the proton. And if we consider the reaction that is the backward reaction, when the products of the forward reactions are acting as acid and base, so the species which have been generated from the acid is known as conjugate base. Why? Because it will donate the proton to convert to the water. So it is actually acting as a acid because it's donating the proton, but this one will accept the proton, so it acts as conjugate base. Note that this reaction is an equilibrium reaction, and most acid-base reactions are equilibrium reactions because the reactants only partially ionized. Strong acid and base is ionized completely in water. Weak acid and base is ionized partially in water and acid. So an acidic aqueous solution is any solution with concentration of hydrogen ion is greater than 10 to the power minus 7 molar. For acidic solution, the concentration of the hydrogen ion or the proton or the hydronium ion is actually greater than 10 to the power minus 7 molar, and the concentration of hydroxyl ion is less than the concentration of proton. Similarly, for the basic solution, the concentration of the hydroxyl ion is greater than 10 to the power minus 7 molar, but the concentration of the proton is less than the concentration of hydroxyl ion, and overall the concentration of the solution must be equal to 10 to the power minus 14 molar, adding the concentration of the proton and hydroxyl ion. So to determine the relative strength of an acid or base, we need to find how much the acid or base ionizes or dissociates. This is needed because the strong acids or bases that are completely ionized, it means that the ionized species are higher for the strong acids and bases. Conversely, we can say that the number of protons that are generated from the dissociation of the acid are higher for the strong acids, whereas for the weak acids the dissociated species are less due to the partial ionization. So in order to find out how much the acid or the base ionizes or dissociates in water at equilibrium, the equilibrium constant known as K equilibrium gives this information and defined as follows. The equilibrium constant for a particular reaction is given by the product of the concentration of the species that are on right side of the equation over the product of the concentrations of the species that are on the left side of the equation. However, because water is the solvent and its concentration is essentially constant, a more meaningful value for acid ionization comes from multiplying the equilibrium constant by water concentration. So this Ka is actually known as acid dissociation constant, and the value of Ka specifies the strength of the acid. The stronger the acid, larger the amount of dissociation and the larger the concentration of hydronium ions. Thus, the stronger the acid, the larger the value of Ka. Strong acids completely dissociate in water and have large dissociation constants. Most organic compounds are weak acids and have dissociation constants in the range of 10 to the power minus 2 to 10 to the power minus 60. So usually we get a large range of the Ka values for their dissociation constants. So it's often conversion of logarithmic scale from the simple Ka scale is similar to the conversion that is for the pH, that is the concentration of hydrogen ion. By taking the negative log of the hydrogen ion concentration gives the value of pH. So similarly we can take the negative log of base 10 for the Ka value, that gives the value known as pKa. So the pKa is the value that determines the strength of the acid and bases. But usually it is more important for the acids, and for bases we will discuss about the pKb values. For strong acids which are completely dissociated into the hydrogen ion and the counter ion, the value ranges between 0 or below. Peak pKa value is usually given relative to the water. Values higher than 18 and lower than -5 are usually estimated, which cannot be usually calculated through experimental determinations. So in the scale of the pKa values, different acids have been distributed, showing the maximum acidity of the mineral acids like hydrochloric acid, sulfuric acid, etc. Now let's solve the Ka and pKa values for water. So now let's discuss again the autoionization of water. It means that one water molecule is acting as an acid, the other water molecule is acting as base. So one is donating the proton and the other is accepting the proton to give the concentration of the hydronium ion and hydroxyl ion, that is actually the proton. So the concentration of the two species is actually -7 molar. And according to our previous discussion, that the Ka of the water is calculated from the concentration of the hydronium ion and concentration of hydroxyl ion over concentration of water. And the molar concentration of the water is unknown, whereas the concentration of the hydronium ion and hydroxyl ion is 10⁻⁻7 molar. For the calculation of this one, now let's consider the equilibrium constant for the water that was considered 10⁻⁻14 in previous discussion. So we can substitute the value of 10⁻⁻14 for the numerator of Ka expression, and the concentration of the water must be given in number of moles per liter, and that is calculated as follows. So the concentration of water is actually the weight of 1 liter water over molecular weight of water, that must be equal to 1000 gram per liter, that is the weight of 1 liter of water, and the molecular weight of water is 18 gram per liter, that must give the value of 55.6 mole per liter. Now we can substitute the value of the concentration of water in this equation. So the Ka value is actually equal to 10⁻⁻7 into 10⁻⁻7 molar over 55.6, that is equal to 1.8 into 10⁻⁻16. So Ka value is actually equal to 1.8 10⁻⁻16 for water. So if we take the negative log of Ka concentration, the pKa that must give the value of 15.7. So the value for water is 15.7. It is showing that the solution is neutral, and variation from this value gives the acidic or basic solutions. A strong acid always reacts to form a weak conjugate base, and a weak acid always reacts to form a strong conjugate base. This relationship exists because the stronger the Lowry-Bronsted acid, the more willing it to give up the proton, thus forming a more stable conjugate base that do not want to change to the acidic form by accepting the proton. So the more stable conjugate base is less willing to accept a proton. So for the strong acid, the right side of the reaction is favored. At equilibrium, the right side is actually a stable base but weak, as it is less willing to accept the proton. However, dissociation of ammonia is very unlikely to occur because the amide ion is very strong base. Thus, at equilibrium, the left side is favored. The relationship between a base and its conjugate acid is similar to that of an acid and its conjugate base. Strong bases form a weak conjugate acids, and weak bases reacts to form a strong conjugate acids. The reason for base strength are the opposite of the reasons for the conjugate acid strengths. For Lowry-Bronsted base, the stronger the base, more willing it to accept the proton. An extremely important concept in predicting the outcome of a reaction is that position of the equilibrium is on the side of weaker member of the acid conjugate base or base conjugate acid pair. A strong acid or base is more reactive than a weak acid or base.